Good morning, everyone. Welcome to our SPE Live on Diagnosing Fractures in Unconventional Reservoir Completions. Today, we have gathered a group of leading experts in the area of fracture diagnostics to discuss why these techniques are important and how we drive value and impact from these technologies. In the panel today, we have Kyle Haustviet from Devon Energy, Mike Mayerhofer from Liberty Oilfield Services, David Craig from Oxy, and Paul Weddle from Tapper Resources. And my name is Jessica Iriarte, and I'm with Weddle Data Labs. So I'll do a brief introduction of the panel, and then I'll start with the questions. Fracture diagnostic techniques are used to peek into the earth to better understand hydraulic fracture growth and orientation, cluster performance, and well interactions. Ultimately, these help us determine the design parameters that need to be optimized to improve stimulation effectiveness. Today, this comprises of some of the most advanced technology applications in shale development, involving high-resolution sensors, high-frequency data, signal processing techniques, and advanced interpretations, combined with cutting-edge visualizations and data analytics. So with that, I would like to start our panel. And for that, I want to start with why. So Mike, why do we run diagnostics, and what questions are we trying to answer?
Yeah, hello everybody. Thank you, Jessica, for that question. I appreciate the opportunity to be here on this. Why do we run frac diagnostics? Well, one of the key reasons is that we just can't see what's going on underground, right? That's one of the principal reasons when we do hydraulic fractures and produce them, we just can't directly see what's going on underground. That's why we need some kind of frac diagnostics. In the beginning, it all started with, simple frac pressure diagnostics and so forth, but we needed something more. So, in the late 80s, 90s, there was a lot of effort by GRI, Department of Energy funded projects, to kind of develop better direct fracture diagnostics. And a lot of work was done with drilling through the hydraulic fracts. That's where the birth of microseismic, technologies happened to do the far field diagnostics. So that was really the key. And the most important thing was, initially just the basic understanding of frac geometry. How long are these fracts? How tall are these fracts? What's their azimuth? Which direction are they growing? Are they vertical? Are they subvertical, horizontal? Those were some of the key questions. As we moved to the unconventionals and the shales, some other things, came up, like, are these fracts simple planar fracts? Are they complex frac networks? That was kind of the initial eye-opening experience in the Barnett Shale, for example, that these fractures aren't just growing in one direction, they're going in multiple directions in complex kind of frac networks. So that's really, kind of the basic understanding. But these days, I think the most important questions are really related to, what completion and frac design, works the best in a certain area. What is the best cluster spacing? What is the best stage length that we can maximize, the produced frac surface area, but at the same time, minimize our completion costs, so not go overboard on that. Then how can we optimize, this cluster perf efficiency to ensure that we're treating every perf interval? How can we maximize the limited entry or diversion, et cetera, to achieve that objective? Then also when it comes to well spacing, given a certain well spacing, both parallel and staggered, what is the best, treatment size that I need to pump to achieve, an optimum kind of drainage pattern? And then also maybe change the well spacing, according to that. How do I optimize that whole process? And that's really where frac diagnostics have to help to get that basic understanding of, frac geometry and interaction. Another question that always comes up is the sequencing of wells. How does the sequencing of the wells, the zipper fracking, how does that affect the overall frac surface area that I generate? And in some areas, there may be questions on, growing into zones that have, unwanted kind of production response, excess water production, H2S. How do I minimize the height growth into those kind of formations? Vice versa, it's also when I land my well in a certain, very thick, let's say, unconventional reservoir, how do I maximize the height coverage through that zone? These are some key questions. When I stagger my laterals, what is that interaction of the frac height between the laterals? What is the best landing zone based on a wine rack pattern? So these are some of the key questions that we're trying to answer. And then as we move straight from, just the hydraulic frac geometry diagnostics, it's also then it goes over to the production diagnostics. What is really effectively producing? Are all these clusters effectively producing into the well? Does the contribution of the clusters change over time? When wells are wells interfering with each other? And if so, does that change over time? Does that change how the clusters are contributing, the stages within the well? These are all questions we're trying to answer, with diagnostics. Protect, another key thing that we're trying to figure out, how do we best protect wells from being negatively hit by, new completions of child wells? Frac diagnostics help with that kind of question too. And then on the simpler side, on the traditional side, we've always had frac diagnostics such as DFIT, diagnostic fracture injection tests, trying to answer the basic questions of what is the closure stress in the rock, because that's just a key parameter that we feed into our frac models. What is the pore pressure in the area, which obviously goes into, the production side, the reservoir side of things and understanding. So these are all the key things, because in the end, we run all these frac diagnostics, but we really need to feed that information into models, because we need to do it on a larger scale to be able to optimize applications and the production. So that was kind of in a quick, nutshell, my kind of view on why we run these diagnostics.
Thank you, Mike. And you mentioned a little bit when one of the techniques and when it started. And I would like to shift to Kyle now and talk a little bit about what's the history of diagnostics, where it started and where we are now.
Thanks for the question, Jessica, and great job, Mike. I think you highlighted a lot of the key points. I'm seeing names pop up in different locations on the bottom. Welcome, everyone. Thank you all for tuning in. Specific to hydraulic fracturing, it began in 1949, the first job, and we collected data at that point. Like Mike said, some of the most frequently gathered data is simply treating pressure, treating rate. Fast forwarding a couple decades, not to downplay a lot of great work that occurred in that time frame, but a major breakthrough occurred during a project funded by the DOE, which was partnering with Sandia National Laboratories in Nevada, and the project was coined the Mine Back. This was one of the first times we really get to see what a hydraulic fracture looked like in the subsurface. The well was drilled in the mesa, hydraulically stimulated, and then they drilled a mine through it. And they got to look at the hydraulic fracture and understand how it grew and how it propagated, and was it vertical, was it horizontal, like Mike was referencing. Norm Warpinski was one of the individuals involved, and from that published a ton of groundbreaking work, figuratively and literally. That project changed the way that we envision fractures and understand how they grow, and it fed into more diagnostic development like microseismic. The DOE is still funding projects today, a lot of which have continued to advance our knowledge. HFTS2, the hydraulic fracturing test site number 2, was completed in the Delaware Basin in the Wolfcamp a couple of years ago, and that data is going to be released this year. Moving forward a little more, as we transition into modern multi-stage hydraulic fractures and horizontal wellbores for unconventionals, the shale gas boom in the early 2000s really accelerated a lot of new diagnostic growth. The frac that changed everything, it was coined by Pinnacle at the time, was one of the first successful and most well-known commercial applications of microseismic. That was deployed in 2001. We've seen microseismic continue to grow and develop. Advancements in logging and geomechanical testing of our core has improved our understanding of stress profiles and fed into our frac models that have been tweaked and altered from some of our conventional understanding. Today I would argue that optical fiber is probably the most advanced and has the most upside still today. It's a tool that Shell adopted early on and focused on DTS, or the temperature sensing. It's used by geophysicists for improving their seismic profiles, for gathering microseismic data. It's used by completion engineers for understanding how are fluids being distributed across the lateral, trying to improve that distribution, like Jessica and Mike referenced. It's used for cross-well strain to understand how wells are interacting with one another, so that feeds into the well spacing and completion design relationship. It's used to understand flow during the production period. I would throw that out to the audience. That's probably one of the biggest needs right now, is a low-cost, dependable production log on the lateral for unconventional. So I think there's still a lot of work to be done there. It's used by production engineers to optimize gas lift, to optimize refracs, chemical remediation. There's so many use cases for fiber right now. I think it's the Swiss Army knife of diagnostics. So many applications. The last one I'll mention is offset pressure monitoring. There's really three buckets. There's watching pressure from a completed well that's been producing. There's monitoring pressure from a well that's a new completion or being completed as part of a multi-well zipper. And then there's sealed wellbore pressure monitoring. Each of those types offer unique measurements. And one of the things I really like about this diagnostic is its scalability. It's low cost. Normally that data is collected with a surface gauge, so very low operational risk. That low cost nature makes it very scalable. And I think this is going to help us continue to progress towards real-time completions. How do we start to refine at a stage level to make sure we're adding the most value, putting the right recipe on each stage, and adjusting for rock variability or mechanical variability, whether it's cement or plug variability. So I think those are some of that's kind of the progression. Tons of diagnostics have been developed and improved and expanded on in between there. Just wanted to hit on a few of those.
Thank you, Kyle. You mentioned a lot low-cost techniques, and I would say that's definitely something that we all in the industry always are looking for, especially when we're trying to move towards cost efficiency and optimizing operations. So now I'd like to talk a little bit about some of these specific diagnostic techniques, and I would like to ask Paul, what are some of these more affordable diagnostic techniques that we have, since we're talking about low cost, and what's important to learn early versus often?
Yeah, I think, for me, I've put out some papers in the past, but there's a lot of really cheap data we can get on a lot of stages very quickly, whether that be step-down data, tying that to the geologic or geosteering profile. And I think it prevents us from, when we can sample a lot of data points, it really prevents us from jumping to conclusions or getting tricked by an outlier well, either your worst well or your best well. It's amazing how many times I've done big diagnostic projects on a well that ends up being an outlier one way or the other. And it's years later that we figure that out. And so for me, like I said, I've talked about step downs and then tying it to the geosteering solution, and then as well as the production solution, whether that be A root K or pressure normalized rate or RPI, whatever you want to call it. But doing that on a lot of wells in a major way so that you can actually see trends through time and of statistical significance for very little dollars on every well, that can add up to a very meaningful tool to guide your next steps. Some other stuff that comes to mind is just, in the last, 5-6 years, you've been able to weigh the amount of sand that you're producing back for a different choke schedule on different wells. There's a lot of data out there now you can gather through, desanders that actually capture and weigh that, having your guys in the field on the production over a long period of time, telling you when they're cleaning out their treaters, trying to quantify that kind of information. It just allows you to really tie together multi-disciplines at a very cheap level to actually answer those questions when they come up, or, in 6 months' time on a new play or new formation. It allows you to already have the data in hand that you can then kind of cross-compare and relate. And then the only other thing is, there's been a lot of advancement in downhole tracer technology, and, we're kind of constantly looking at what's the most effective way to get, in a 50-stage well, get 50 data points, from whether it be lithology differences or be completion differences or fluid chemistry or additive differences that you're doing throughout the well. And so getting 50 data points out of one well instead of just a full well trial your ability to learn quickly and move forward. And so that's kind of the bucket of tools, and the way I think about things is if you can spend a little bit money on your first, a little bit more money on every stage, your first 10 wells can be extremely impactful to guide your next 10 wells. So
I would like to move to David now and ask you, if you're going to pair various diagnostics techniques, we've been talking about tracers, monitoring wells, fiber optics, etc., or maybe others, what are some of the best or most complementary diagnostics in your opinion?
Thank you. First off, I'm very happy to be here. Thanks for inviting me, and thanks for the question, Jessica. And I'm actually honored to be on with Mike, Paul, and Kyle. So it's a pretty good group of people that SPE has gathered today. And I like to think of this, if we're in particular looking at fracture geometry, then I split the problem into near wellbore versus far field. So I would like to be able to diagnose the type of cluster efficiency I have near wellbore, for example, but I would also like to see in the far field how many of those clusters are growing out, couple of thousand feet away from the wellbore. So when I talk about picking or pairing diagnostics, oftentimes that's what I'll look at is how do I pair near wellbore with far field? And then it comes down to budget. If I've got a really excellent project with good funding, maybe it's a project with other operators, we've all gone in together, for example, like the hydraulic fracturing test site, then I can run fiber optic cable in my treatment well. I can run fiber optic cable in the offset well bores, and I can look at fluid distribution during fracturing in the treatment well, but I can also look at strain rate data in the far field, and I can see those fractures grow and cross the well bores in the far field. Now that's kind of at the expensive end of the spectrum. What if you don't have that kind of budget? You're a smaller operator, but even though you're a smaller operator, you still have the exact same questions. Well, you can still tailor your diagnostic program to provide some of these answers. Radioactive tracers can still be an effective technology for looking at cluster efficiency near wellbore, for example. One of the things that I like to do is use innovative tracer programs where you're not just tracing everything, you take snapshots in time. So you trace the first 100 barrels of a stage and the last 100 barrels of a stage with different isotopes, and you look at what your cluster efficiency was at the beginning of the stage and at the end of stage. And when you do this, you'll find that it changes. So, but that is actually a very inexpensive diagnostic to be able to perform. And then in the far field, one of the techniques that I found has been extremely helpful is if you're drilling your offset wells after you fracked the original treatment well, just run an image log when you're pulling the drill pipe out of the offset well, record that image log and look at the hydraulic fractures. You can actually observe the fractures that were created from the treatment well in the offset well, and oftentimes you can trace those fractures back to isolated clusters in the treatment well. So neither one of those last two pairings of radioactive tracers and image logs, that's kind of at the low end of the spectrum on cost to the operator, but it still provides a similar, if not as good answer as you would obtain from using the high end of the cost spectrum, which would be fiber optics in both wellbores. You are limited though, because you're getting snapshots in time versus continuous data. So there's a couple of options for pairing diagnostics.
Thank you, David. And we do have a question in the chat from Jorge Ponce. It looks like cluster effectiveness is the key to get good productivity. Besides fiber optics and downhole camera, are there any other technologies to assess how much each cluster is making? I think some of you have already mentioned some of that, but if any of you would like to add any comments.
Well, I'll go ahead and add to it since to assess how much each cluster is making. So that's kind of a different problem because when I was talking about it previously, I was looking at the distribution of fluid during fracturing in individual clusters, but this is the other side of the problem. Just because we had fluid going into a cluster during fracturing operations doesn't mean we're going to have hydrocarbons coming back out of that cluster during production. So this is another set of diagnostics that we would need to look at. There are some interesting production logging techniques that can be run to look at contributions from individual clusters. Again, at the top end of the spectrum, you have fiber optics, which is probably the best diagnostic for looking at that inflow. And then the conventional tracer logs can also be used. One of the issues when you use the wellbore diagnostics or inside the wellbore diagnostics is behind pipe flow. So because of the complex nature of the fractures at the wellbore, in other words, there can be components of fractures that are longitudinal, then turn and create transverse fractures. And for those of you that have looked at some of the work DOE has done on the very complex initiation patterns near the wellbore, you'll kind of understand what I'm alluding to here. But because of that, where you have inflow into your horizontal well may not represent where that fluid originated. That fluid can come from somewhere else along the wellbore, migrate up through this complex fracture pattern around the wellbore and into the well. So it's a little hard to use inside the wellbore production logging to always be able to establish this answer of which fractures are the most productive. And that's a lot for me, so I'll be quiet now.
Thank you, David. So I'll go back to some of the questions that I had for you all. So once we have, we talked about several diagnostics techniques and what are the benefits for some of them, how it has evolved. Now, once you have run these techniques, how do you apply these learnings moving forward? And I would like to hear from Paul and Mike on this. How do you take these key learnings back to the assets, and how do you ensure that they're distributed throughout the organization?
I've got a relatively quick answer to that. I think a lot of it has to do with trying to measure, diminishing returns and thinking about the Pareto principle, in terms of what matters and what truly moves the needle versus what really might not move the needle that much or might have a lot of argument based on your geological and your kind of normal statistical variation. And so at least what I've kind of found is spending quite a bit of time with the asset team, defining what you're changing and why, and really letting them kind of weigh in and question, as well as help you assess the data. And we just went through a big A-root case study on a bunch of recent perforating changes, and there was a lot of skepticism, and but after drawing on the whiteboard for a couple hours and letting them run with it, we all got to the same answer, which was pretty encouraging. And now everyone's much more excited going forward. So kind of figuring out how to collaborate, how to give people space to wrap their head around the ideas you're trying to push, and what the impact could be. And then also just making sure it's a two-way street and listening to their concerns. And, economic risk, saving dollars makes a lot more sense at $40 oil than it does at 65. And always just being very aware and open-minded to, both sides of the equation. So.
Yeah, from my side, I think Paul covered it pretty well. But I think one of the key things, and we've seen in the past with diagnostics, is they can be pretty expensive and pricey. The key thing is always to make sure that the value you get out of it is actually realized. It just doesn't become a science experiment that gets shelved somewhere. You have to follow through with some action items. And as Paul said, a lot of it is a discussion within the teams of a company to kind of come up with, different completion strategies, test some things out in the field, get some feedback from that, and kind of come up with the best optimization, when it comes to the completion sites. So I think that the follow through is key. And then for me, also coming obviously from the modeling side, the key thing is to get these diagnostics into, reasonable frac and reservoir models, to calibrate those, and then to play these what if scenarios. What if I increase the treatment size, I double the treatment size? What if I change my cluster strategy, to 10 clusters instead of 5 clusters? How is all that going to affect, the frac geometry and frac conductivity and all these other things, and the production in the end, right? So we do need models to kind of bridge that a little, and in my opinion, that's how you realize some of that additional value, is by using and then of course confirming it, with your field results.
Thank you, Mike. I do have a follow-up question to that, and any of you can take it. Once you have, some of these learnings and you document them, how do you allow, or how do you ensure that they are saved or they are collected in a format that allows for future team members to review them, and both the raw data and the interpretations, and make use of those learnings?
I'll take part of that, Jessica. I'll take the raw data part. David, I'll leave the more structured PowerPoints and other data for you. But for the raw data, we've invested a lot of time and resources into developing a time-based historian that we store all data, drilling, completions, production. So it's easily accessible. We have formatted our framework, so accessing any well across the company, it's the same framework to drill down to that specific data stream. That's a large undertaking. It took several years, and finding the right historian and the right viewers and the right analytics tools, all of that takes time, but it definitely adds value after you get to that point. On the geologic side, Paul and Mike both talked a lot about the team. I think that integrated team concept is critical to make sure that we understand the biggest questions, and then we bring forth the right diagnostics, not the other way around. So for the geology side, a lot of that is structured in a similar way, similar access points, similar drill down options to access any log data for any well across the company. So that consistent structure is key to make sure that anybody can switch an asset, switch an operating area, and still access the same data they're used to using to build their models, to evaluate their completion designs. And yeah, so access is key for data, and structure is. I'll let David take the second half.
Thank you, Kyle. Hey, I'm kind of the elder statesman on the panel, and I hate that it's gotten to that, but it's true. And so one of the things, and Jessica, this is really a great question. This is something that I struggle with constantly, but we see lessons learned being repeated in cycles. We've already solved this problem 20 plus years ago, but the new generations of engineers haven't seen that problem from 20 plus years ago. So to them, it's new. And so there are a couple of ways to deal with this. One of the ways is keeping elder statesmen around so we can help try to prevent recycling old problems. So that's a plug for me. Yay, keep me around. The other one is, hey, let's use modern technology. What we're trying to do now is video. We can record 5-minute videos that I'm not plugging YouTube, but there's a platform that made the 5-minute video famous. But if we can inside our companies record these little videos that talk about these issues, then people are able to watch those on their phone, even on a location. You can pull up a DFIT question on a location, watch a 5-minute video of a DFIT problem that was solved 25 years ago. So that's the way new technology is helping us to make sure those lessons learned are actually stored and utilized going forward. But I can't overemphasize the importance of keeping the elder statesmen around for a long time.
Thank you, David. We are having a lot of questions coming in the chat, so I'm going to address a couple of those. From Dante Guerra, we have, as our cluster spacing becomes closer, how do we tie back fractures from far field image log to the origination cluster, especially considering potential fracture complexity?
I'm assuming this one's going to be for me since I brought this up. And that's a really good question. And it's a question that hopefully we'll answer at ERTEC this summer. We have done studies in multiple fields using image logs. And the one thing that, and we've also done studies in multiple fields with fiber. And one of the observations that you can make is that in many of these fields, we do have essentially planar fractures that are growing out away from the wellbore at long distances. Now, that doesn't mean there isn't some level of complexity, because when we look at image logs, we can see that a planar fracture grows as a in echelon swarm of fractures. So you have to understand there is still a little complexity there, but essentially the fractures are all still planar. And so you can try to just use the correct fracture orientation to trace back to the cluster that may have originated that fracture. But you bring up a valid point. At some point, at some distance, you don't have enough resolution to be able to tell for certain which cluster that fracture came from. And the example I'll use is HFTS2, and at the ERTEC paper, when we go through it there, HFTS2, I think we could correlate 90+% of the fractures, okay? We were at 30-foot cluster spacing. But in the Turner Formation in the Powder River Basin, we're at a little bit closer cluster spacing, and there we could correlate fractures from stages, but our percentage of correlating fractures to clusters fell to about 50 to 60% in the Turner. It just became much more difficult. If you go down to 10-foot clusters, yeah, that's an additional level of difficulty that you've added to the problem as far as being able to correlate those. And for something like that, you probably are going to have to look at fiber to give you a little better resolution in achieving the answer. Hopefully that addressed the question.
Thank you, David. So for our last question today, before we address some of the other ones we have in the chat, I would like to talk about what's next in the realm of diagnostics. Where are we with real-time diagnostic, and what's the value gain of diagnostics in real time? Kyle and David, well, any of you, Paul, if you want to chime in. I would also like to hear if any of you has an example of the return of investment for a diagnostic project. For example, if you could tell me, you know, we did a project A that cost X amount of dollars, but we were able to make design changes, whether they were real time or near real time, where we could save Y amount of dollars.
Yep, I'll start off with what's next and address the case study and a little bit of the savings. I think the big what's next is making changes in response to these measurements in real time. And I think that's going to come soon. We've tested it. Last summer, we tested our first handful of stages using offset pressure monitoring, and we use that data, the responses, in order to make changes on the fly. Again, every stage treats differently. All these questions that we're hearing, it's how much fluid is each cluster taking? How do we know the variability? Well, that changes every single stage. And it's a function of a lot of things that we're not always able to control or engineer around. So the other piece of this puzzle that we're trying to solve is when we can't control some things and there is variability that's occurring in the lateral, how do we respond to that in order to maybe we increase volume if prices are right? Like Paul said, there's two sides of the equation, $60, $70, $80 oil. It might make sense to invest more capital in a stage that's treating well. $30, $40 oil, it's probably a better decision to try to control costs. So if you have a runaway fracture that's communicating in the far field very early on, it makes a lot of sense to reduce the capital spend on that stage. In our case study, 5 stages were monitored. We reduced the volume of fluid and placed the design amount of sand. So we gave some control and power to our folks in the field. We said, if you know how this formation's taken the treatment and we see a response before some predetermined volume pumped, go ahead and place that sand with less fluid. Really, this was a test to understand what's that time lag between taking a measurement in the field, getting it back to our system where we can process and make the recommended change, getting that recommended change back to the field and executing. For us, we saved approximately 10% of the stage cost, and we were using a surface pressure gauge. So very low cost, resulted in savings for 5 stages. We're working to scale that and understand how to push that across more of our completions and drive those savings throughout. But again, what's next? Just using our data more effectively and in a more real-time sense.
I'm going to jump in and add one thing. I don't want to talk too much, but and you know, Kyle, I love you. I'm going to take a little different approach on this one. In my opinion, the industry, and again, this goes back to the elder statesman, the peak of real-time decision making to me occurred in the 1990s when everybody had computers on location and was running Frac Pro in real time and trying to make real-time decisions on sand concentrations and packing the frac and all the other little sayings that we came up with at the time in order to effectively stimulate these tight gas sand reservoirs. At the time, that's what we were working on. And you know, in hindsight, we look at that and go, we were trying to apply the best technology in real time, but I'm not sure that we did, that we had the best interests of the wells at heart. If we look back at it historically, maybe now we would have done it differently than we did then. And I'm seeing a trend in the industry, and I'm not speaking for Oxy here, but just a trend in the industry to move not towards real time, but actually moving further away from it and going to more of after the fact type engineering. You know, we're having few engineers that actually monitor fracturing treatments on location. There's some effort at doing remote monitoring, but not very much. So generally, if you have to apply engineers to do that type of monitoring and making real-time decisions, you're actually changing the cost structure too. So you're adding costs, and economics have become so important that unfortunately, I think economics may drive real-time decision-making out of hydraulic fracturing unless there's a specific scenario. For example, you're trying to avoid a water zone or something like that. That there are cases where it can work. But by and large, I think the opposite may be true.
That's interesting, David. I would say that, there are so many technologies now that make real-time monitoring so much easier without having to increase in the number of people looking at or monitoring the data, right? Like machine learning, data science applications can help you with that, making it way more cost-effective. I will move back to some of the comments because we have a very engaged audience today. So I will address Ken Allison's question. Is your company taking the data you gather and using it to calibrate a fracturing reservoir simulator? And is it working to help you optimize the well spacing and fracture design?
I'll jump in. Yes, we are. Courtney Brinkley just published a paper. I think they released this week for the frac conference, and we document a case study in the Eagle Ford where we use offset pressure data in order to calibrate our frac model. We've done this in multiple basins. We then feed those geometries from our fracture simulator that we've calibrated with the data, like Mike has referenced, into our reservoir simulator. And then we match reality, and then we use those two calibrated models to run iteration sensitivities on what ifs. What if you adjust staggering, spacing, completion design? So that's become a common practice for us, Karen. Good question.
Yeah, so I can say the same from my end. So we definitely have a lot of requests to, do this kind of follow through, because I do think that is the key thing. Following through on the diagnostic information is to do these sensitivity studies, right? To kind of optimize going forward. So.
Thank you both. Another question from Lean Helms. Have any of you worked using reservoir simulation and history matching behavior during pumping and fall off to evaluate things like changes in reservoir parameters due to fracturing and perforation cluster efficiency?
I can briefly address that if I understand the question right. Changes in reservoir parameters. The only thing that comes to mind for me is, are we doing anything to enhance, the natural fractures, and are we by that, changing the deliverability of the rock in a certain way? So that would be my main thing. The other things we may be looking at are not really related to reservoir parameters changing as much. So I would just say, the hydraulic fracture parameters themselves that we're looking at. Obviously, one of the things that we haven't discussed, besides frac geometry is frac conductivity. That is one of those elusive parameters in fracturing that we can't really measure directly downhole underground. There are some techniques from a pressure transient analysis point of view that we used way back 20, 30 years ago. We did a lot of pressure buildup testing, even in tight rocks with hydraulic fractures, kind of try to get a feel for what the hydraulic frac conductivity is. But of course, these days with our long horizontal wells, lots of frac stages, it's very difficult to do a unique, pressure transient analysis of a horizontal well and figure out exactly what the frac conductivities are at any given cluster, et cetera. So that becomes a little more difficult there. But I don't know if anybody else has any other comments on that.
Yeah, I guess I'll jump in. I've worked some of these projects with the help of Mike and his team over at Liberty, and it's been directionally very useful in trying to go back and determine, hey, are we in the right ballpark? Do we think we know our cluster efficiency? And if so, does it generally match a reasonable history match? And then what do we do to make it better from there? Again, there's a lot of non-uniqueness out there, but if you're consistent in your assumptions and you're really just trying to measure a relative performance gain, the absolute values don't always matter as much as some people might like to believe. It's the directionality of the improvement. And so that's where I've had a lot of usefulness, again, working with Mike and some other folks on that kind of project exactly, specifically in regards to perforation cluster efficiency and well performance.
Thank you. Where we are in our 45-minute mark, and I want to be respectful of everybody's time. Thank you so much for this very insightful conversation. I've been so honored to share this panel conversation with all of you. Thank you all again.
Thank you.
Thank you very much.
Thank you.
Appreciate it.